Hello students, welcome to my channel. Today we'll learn about measurement of length by using parallax method. Now there are two kinds of measurements. One is direct measurement and another is indirect measurement. By direct measurement we mean that we can use an instrument directly to measure the length or distance of a certain object. For example, if the length falls between 10 to the power minus 3 meters to 10 to the power 2 meters, then we can use a meter scale to measure this length. But if the length is smaller, for example up to 10 to the power minus 4 meters, then we use vernier calipers. If the length is further smaller, for example between 10 to the power minus 4 to 10 to the power minus 5 meters, then we use screw gauge. So this means that here we can use the instrument to measure the length or distance directly with the help of that instrument. But how about the distances which are much larger than these distances? For example, the distance of a planet from our Earth. In that case, we cannot take a meter scale to that planet to measure the distance of that planet from our Earth. So in those cases, we use indirect methods of measurements. By indirect method of measurements, we mean that we make some approximations and do some calculations to calculate the distance of that planet from our Earth. One such method is called parallax method, and today we'll learn about this method. Now, what is parallax method? To understand this method, let us do a small exercise. Take a pen or a pencil and hold it with your hands in front of your eyes, and in the background take a reference point. Let us assume that this is our reference point with respect to which we want to see the position of our pen or pencil. So let us hold this pen or pencil in front of your eyes like this, and then you close one eye, left eye for example, and then see how the position of the pencil has shifted. You will see that when you have closed your left eye, the position has shifted little bit towards the left, and when you have closed your right eye, the position has shifted little bit towards the right, and when you have both the eyes open, it is in the middle. So let us draw and understand this in further clarity. For example, suppose this is a pencil you are holding. And these are your eyes. So when you have both the eyes open, you look at the pencil, you will see it here with reference to this point. Now you close one eye, for example you close your left eye and look at the position, you will see that the position has shifted little bit towards the left. And then you close your right eye and then observe this position of the pencil. You will see that it has little bit shifted towards the right with respect to this point. So left eye closed, position has shifted towards this side. Right eye closed, position has shifted towards this side. Both eyes open, it is in the middle. Now this effect is called parallax effect. And we use this parallax method in the measurement of astronomical distances in the universe. For example, if you want to measure the distance of a planet or a star from Earth, you calculate that distance with the help of this method. How? Let us understand. Instead of these two eyes, let us assume that these are two telescopes at position A, and this is telescope at position B. And these two positions A and B are at the opposite ends of our Earth. Let us assume that this is our Earth. This is our Earth. And these are 2 points on the opposite ends of the Earth. So we make one measurement from point A with the telescope and second measurement from point B with the telescope. And let us assume that this is the planet. Instead of the pencil here, we have a planet now whose distance we want to measure. So let us assume that this is the planet S, and we want to measure its distance from Earth. And so we make use of this parallax method. Like we closed one eye, and then we closed left eye, then we closed the right eye, and saw how the position shifted. Similarly with the telescopes, we will see if we use only one telescope and do not use this telescope, we use only this telescope and see the position has shifted little bit towards this side. And then this eye closed means this telescope closed, and we use this telescope from point B and then look at the position of the planet, and we will see that its position is shifted towards this side. And when both the telescopes are working at the same time, if we observe the position of the planet at the same time, then this is the actual position. But with one telescope shut down and the other working, the position will be shifted either to this side or to this side. And then we measure the parallax angle. What is parallax angle? Now if from the line of sight, this is a line of sight, if this is not working, let us say that this eye is closed, this is open, and we draw a line here from this point to this point, this is called line of sight. Similarly, when we observe from this side, this is a line of sight. And the lines where they meet each other, where they merge with each other, this is the point. And the angle which is formed at this point, this is called parallax angle. So in this case, this is the actual position. So if we draw a line from the actual position of the planet to point A, and another line from the actual position of the planet to point B, then the angle between these two lines will be theta, which is the parallax angle. And let us form a triangle and draw a line here too. And this distance between points A and point B is called B. This angle theta is called parallax angle. Theta is parallax angle, or angle ASB. Angle ASB is equal to parallax angle, which is always in radians. Let us say that the distance between our Earth and the planet is d. We know this distance between these 2 points. We have calculated parallax angle theta, and we want to calculate this distance d. So theta is known, b is known, and we want to calculate d. Now to calculate d, we make another assumption. The assumption is that this planet S is in the center of a circle. Now if this planet S is in the center of a circle, then this distance becomes the radius of the circle. Let me draw, like if this is the center of a circle with radius d, then the circle will be something like this. So assuming that this is in the center and distance between A and S, that is Earth and the planet, is d, which becomes the radius of the circle, and this angle in this case is theta, then A length AS, which is equal to d, and AB is equal to b, AS is equal to D is equal to BS. This distance and this distance is same, so BS is equal to AS is equal to D and AB is equal to B. Here the assumption is that points are much closer. These 2 points on Earth are much closer than the distance between planet and the Earth. So D is much greater than B. This implies B over D is less than 1. So if this is much larger than this, these points are too close to each other compared to this distance. So this means theta is also very small. So theta is small. These are the assumptions. Now we know from the formula of a circle, if this is a circle, this is center of the circle, this angle is theta, and this is arc ABS. Then from the formula of the circle, we know that B is equal to d theta. B is arc of the circle. So arc of the circle B is equal to this radius D into theta. So here in this case radius D is distance between Earth and the star. So from here we can find out B is equal to B over theta. So we have calculated the distance D between this planet S and our Earth using this formula. So now we know the value of D here, that is the distance between our Earth and this planet. We'll use the same formula now to calculate the angular diameter of this planet S. Let us suppose that this is the planet S and these are two observation points A and B here. Now in the first case we took these observation points A and B on Earth, and from two different locations we measured this distance. But in this case now we are taking the two observation points A and B at the opposite end of the planet from a single observation point on Earth. Now, so let us say that this is our Earth and here is the telescope mounted. From the telescope we view one end of the planet B, and then we view the another angle of opposite end of the planet at point A, and let us call that this angle is alpha, and let us call that D is the diameter of the planet, small d. So now we know the angle alpha because from the telescope we measure this point B and point A and we calculate the angle alpha. And we know the distance D because we have already measured this distance D from this formula. So we know the distance D, we know the angle alpha. Alpha is through the direct viewing point via telescope, and D has been calculated by this formula. And then we apply the same formula here and we calculate alpha is equal to D over D, and from here we can calculate D is equal to alpha D. So we have calculated first, in the first step we have calculated distance D. D is equal to B over theta, and in the second step we know D now, the distance from this calculated value of D and the viewing angle alpha, we have calculated the diameter of the same planet, which is D is equal to alpha into D, and alpha and theta are always in radians. I hope it's clear to you now. I hope to see you in the next lecture. Take care. Bye.